Hi everyone, I'm Sarthak. I work with AWS and I'm here to talk about a couple of things. I'll talk about how did we scale Valkey to 1 billion RPS. I'll talk about what challenges did we face, what were our testing methodologies, our profiling, our benchmarks, and in the end, I'll explain why we will not do this exercise ever again. So, yeah, looking forward to that. So before we talk about 1 billion RPS and scaling, let me just give a brief about scaling of Valkey. So within Valkey, historically it started with standalone mode, which basically means that you have one primary and you can have n replicas which are asynchronously replicating from the primary. So what it means is that primary can support the right type of workloads. Uh, but the issue is that primary kind of gets bottlenecked on the write throughput. This type of model scales really well for the read type of workloads, but we still have some problems in, even if we have some beefier machines, we'll still be limited on the write throughput. To solve this, we introduced a cluster mode where we basically can horizontally scale instead of vertically scaling. We have these groups of nodes which are called shards, and each of those shards have their own primary and own set of replicas. And all of these nodes are kind of talking to each other through a gossip protocol, which is basically based on top of cluster bus. I'm mentioning cluster bus right now because it's gonna come soon into the picture. So, what was the problem statement? So, in our earlier experiments, we kind of saw that with standalone, we can easily do 1 million RPS. But can we really scale that experiment to 1,000 times? Can we really go 1 billion RPS? So, with that in mind, the goal was to have Valkey scale up to 1,000 shards. And if we have 1,000 shards, if we have one primary and even one replica, that basically means that there are 2,000 nodes that are gossiping and communicating with each other constantly. And having a Valkey cluster scale is one thing, but it needs to be a little operationally stable as well. What if the nodes go down? Can we recover through that kind of mess as well? So I'll be honest, 1 billion was RPS was just a hook for you guys to be here. It's an absurdly high number, which has very less use cases. I heard that Uber has a use case for this, but we did this. We had a set type of workload using Valkey benchmark for 512 bytes, and with 750 client nodes, we were able to scale that experiment to 1,000 shards. But the challenge was how did the cluster react at 2,000 nodes? So just before I go into that, I'll talk about how did we do it. So we had this cluster benchmark framework that we built on top of the Valkey, which basically spins up multiple EC2 instances for Valkey and client nodes. On top of that, we really wanted granular metric aggregation for each of the nodes, where we wanted to capture metrics like slots covered, what is the cluster state, and how many nodes have failed, how many nodes have marked as failed. And on top of that, we wanted to do profiling as well, because when dealing with so many nodes, it's important to profile and know what is really going on, what is the really bottleneck of it. So yeah, we use R7G.2x large instances and C7G.16x large instances for clients. We had 2,000 Valkey server nodes and 750 client nodes. And we really tested a lot. Our first test case was that in a 1,000 shard cluster with 1,000 primaries, we started with failing one primary and we slowly increased it to 499 primaries. The reason we stopped at 499 was that in a clustering system of Valkey, we need at least the majority of the primary nodes to be alive so that they can make the decision around shard ownership and failovers and things like that. Then we did an experiment with AZ failure where we distributed our nodes, our primaries, our replicas uniformly across 3 AZs, and we just failed a single AZ and just to see what happens. So like 666 nodes were just killed at a click. We started with testing 100 million TPS, which is roughly around 25% engine CPU, which is maybe the normal workload that usually people might have. And we slowly scaled it to 1 billion RPS. We tested with TLS and non-TLS clusters. And we tested with multiple client libraries as well. We tested with Valkey Go, IO Valkey, Glide, Redison, and I'm forgetting, I think, one more. And not just one primary, one replica setups, we tried it with one primary and two replica setups as well. But the thing is, the more primary you have, the more coordination you need, the more decisions on shard ownership becomes complex. So one primary and one replica is more of an extreme setup as well. So while testing all of these scenarios, we kind of ran into some weird issues. I am going to talk about a couple of them in detail and maybe give some other improvements as well. So this is the first one. So in this issue, as you can see on the left side, there is a engine CPU graph where we are capturing all the CPU metrics from all the 2000 nodes. And the first spike that you see is the point where we have killed 499 nodes. And as you can see for the P99 nodes, which is roughly around 2030 nodes, the CPU is gradually increasing, and it keeps up increasing till it reaches 100%. So we really wanted to know what's going on. And on the right side, if you when we did the profiling for these nodes, we saw that there were a lot of connections that the nodes were trying to connect to the fail nodes. Now, when you have 499 fail nodes and each of those nodes are trying to make connections in a single cron cycle, it becomes a lot of compute heavy, and it's taking up as much as all the CPU. And this is not just 20 same nodes. These are 20 nodes which are constantly running into these 20 different nodes which are constantly running into this high CPU. So what did we do? We implemented kind of like a smart connection throttling mechanism where we ensure that each of the fail nodes get a fair chance within the cluster node timeout. But at the same time, we don't want to overwhelm these opening of connections amongst the nodes, amongst the fail nodes. Okay, the second issue. So the two spikes that you see on the engine CPU, you see these are the points, as I said earlier. This is where we killed any of the nodes, like any number north of 450. So when we killed 450 nodes, we saw that there is a brief spike up to 100% and then it comes down, which really irked us because it was a little hard to explain. And the issue was that when these nodes are actually killed, all the other nodes, so in this context, 1500 nodes are constantly gossiping about these failed nodes, and a lot of these nodes which are alive are busy processing these redundant and trying to clean up these failed reports. So in order to mitigate that, what we did was we introduced a radix tree, which was kind of based on top of the report failure time, and we rounded up to a second so that each of the report failure time can kind of have multiple nodes, and it's easier to clean and more efficient to clean. And we saw the results, like it's up to 33.70% as opposed to when it was reaching 100%. I'd like to talk about two more improvements that were really helpful for scaling Valkey. One of them was the shard ranking mechanism. So Binbin from Tencent, he was a Valkey maintainer and TSC member as well. He introduced this shard ranking mechanism where whenever there are multiple shard failures, each of those failed shards will try to request and get the votes. And the issue is that when there are multiple vote requests, the replicas can kind of get conflicted and nobody gets a quorum in which node should be which shard should stabilize first. So we introduced a mechanism where we lexicographically postpone the vote request so that each of the shards can get stabilized. The second improvement is, I talked about cluster bus before, that how it is used for communicating with nodes. Another neat feature is that it's also used for pub/sub messages. And the reason is that client can easily connect to them to send the data and the subscribers can listen to it. The issue was that while we are sending these pub/sub messages, there is a metadata overhead on each of those messages. And that metadata overhead was, I think, around 2 KB. But the issue was that overhead is totally unrelated to the pub/sub messages. It used to have some slot ownership information. So Roshan from AWS improved that to introduce a lightweight header system so that pub/sub messages don't have those information. So with these improvements, I'll talk about the benchmarks for a bit. So the two graphs are basically your average CPU utilization, the engine CPU, and the network throughput. As you can see, from 250 to 2000 node, it almost scales linearly, and it takes about 2.2% engine CPU, and then basically an ideal state where nothing is going on, but just 2.2% is going into clustering. And recovery. while we were killing from one node to up to 499 nodes, we started monitoring these times and how much does it take for a cluster to converge, how much does it take for all the alive nodes to know the exact state of the cluster and converge on the cluster view. So in all our experiments, and I think we ran this like hundreds of times, and we were able to conclude that even in the worst case of killing 499 primary nodes, the cluster is able to recover within a minute. So that was a good find. Now the biggest question, why would we not do this again? So to conclude this experiment, we had to, just to go to 1 billion RPS, we had to start with 2000 nodes and 750, especially C7G.16x large instances. It is just really expensive to run this type of a cluster at this scale, like even keeping apart the operational aspects. But here's a question for you guys. What do you think was the actual cost to run this cluster per hour? Does anybody have a number? Sorry? Public pricing. Yeah, public pricing. Public pricing. Yeah, per hour. Anybody? Yeah, yeah. Okay. Yeah, it's a really, really high number. It's not none of these. It's $2,600 per hour just to run this kind of a cluster. So yeah, it's kind of expensive. So in conclusion, the cluster bus improvements that we made it possible for Valkey to scale up to 2,000 nodes. 1 billion RPS is achievable, and we were able to scale the 1 million RPS experiment to 1,000 shards. And the failovers that we do and the nodes that might go into some issues are bounded, and the recovery is kind of deterministic. So with that, thank you so much. I have just added a QR code for the blog where we describe in more detail the benchmark methodologies that we used. So feel free to check it out. But yeah, thank you.